Imagine a flash so blinding it could outshine 1 trillion suns, an explosion so fierce it punched through 2 billion years of space to rattle our planet's atmosphere. In October 2022, that's exactly what happened. They called it the boat the brightest of all time. I'm Dr. Elena Voss, an astrophysicist at the Voss Observatory, and today I'm taking you on a journey to unravel the greatest cosmic explosion humanity has ever witnessed. Why was it so powerful? What secrets does it hold about our universe? This story will grip you from start to finish, so let's dive in. On October 9th, 2022, the universe threw us a curveball. A gamma ray burst, a sudden blast of the most energetic light known, lit up the cosmos like a galactic spotlight. This wasn't just any burst. It was so intense it overwhelmed every gamma ray detector on Earth, from NASA's Fermi telescope to China's Lhasa Observatory. In mere seconds, it unleashed more energy than our sun will produce in its entire 9 billion year life. That's like comparing a firecracker to a nuclear warhead. What made the boat so extraordinary? It was close 2 billion light years away in the Sagitta constellation, practically our cosmic backyard compared to most gamma ray bursts, which hail from 10 to 13 billion light years out. This proximity gave us a front row seat to a once-in-10,000-year spectacle. The last time something like this happened, humans were still figuring out how to plant crops. But here's the wild part. This burst didn't just dazzle us, it physically touched Earth. Its photons, after traveling 2 billion years, slammed into our ionosphere, the electrified layer 50 to 1,000 kilometers above us, compressing it like a cosmic hand squeezing the atmosphere. It was akin to a solar flare, but from a star so far away, its light began its journey when life on Earth was just single-celled organisms. When I first read about the boat, I was floored. As an astrophysicist, I've studied countless cosmic events, but this one felt personal. It wasn't just a distant light show, it reached out and altered our planet. It's a humbling reminder of how connected we are to the universe, how a star's death billions of years ago can ripple into our lives today. To understand the boat, we need to explore gamma ray bursts. These are flashes of gamma rays, the highest energy form of light, lasting from milliseconds to minutes. They're the universe's most violent events, born from cataclysmic stellar deaths or collisions like the final screams of dying stars or sparks of cosmic crashes. There are two types. Short bursts under 2 seconds come from neutron stars smashing together or merging with black holes, often triggering kilonovae. Bright light shows from decaying elements. Long bursts like the boat last over 2 seconds and stem from massive stars collapsing into black holes, often with a supernova explosion. The boat clocked in at a whopping 10 minutes, a long burst on steroids. The boat was 70 times brighter than any gamma ray burst we'd seen. Its jet streams of particles blasted at near light speed were some of the narrowest and fastest ever recorded. These jets, emitted by the newborn black hole, slammed into surrounding awe, producing the gamma rays we detected. Why so bright? One theory is geometry. If a star spins insanely fast when it dies, its jets become laser-focused, like a flashlight tightened into a spotlight. This spotlight effect makes sense, but it doesn't fully explain the intensity. The sheer number of photons, tens of thousands captured by LHAASO, was unprecedented, like expecting a sparkler and getting a fireworks finale. This suggests something unique about the star or its environment, something our models didn't predict. You'd think a burst this epic came from a monster star's supernova, a detonation so massive it could only belong to a stellar giant. That's what we assumed. But when astronomers aimed the James Webb Space Telescope at the boat's afterglow, they got a shock. The supernova was ordinary. Not a titan, just a regular supernova. This was mind-boggling. A run-of-the-mill supernova shouldn't produce a gamma-ray burst 70 times stronger than anything else. It's like a compact car outracing a Ferrari. What else could explain it? Some propose the boat's host galaxy with low metallicity, fewer heavy elements might have played a role. Low metallicity stars common in the early universe burned differently, potentially creating tighter jets. I think we're missing a piece of the puzzle. Maybe the star had an unusual magnetic field amplifying the jet's power, or an unseen companion star fed it extra material boosting the explosion. These are hypotheses we need to test, but they remind us how much we still don't know about stellar deaths. The boat wasn't just a scientific marvel, it touched lives. Let me share a story from Daocheng, China, home to the LHOSO Observatory. In October 2022, Dr. Li Wei, a lead researcher, was working the night shift when the boat's data flooded their screens. It was chaos, he told me. Our detectors were maxed out and we knew we were seeing history. For weeks, his team worked around the clock analyzing photons that confirmed the ionosphere's compression, a discovery that made global headlines. Then there's Maria, a high school teacher in Arizona. Inspired by the boat, she redesigned her physics curriculum to include gamma-ray bursts. Her students, initially uninterested, were hooked when she explained how this explosion connected to the gold in their jewelry. They started asking, "Could this happen near us?" she said. It made the universe feel alive. These stories hit home for me. Growing up, I was like Maria's students, curious but disconnected from the stars. A teacher showed me how cosmic events shape our world, from the elements in our bodies to the technology we use. The boat reminds us that science isn't just data, it's a human story connecting us across cultures and generations. One of the boat's biggest mysteries is what it didn't do: produce heavy elements like gold. Stars are cosmic forges fusing hydrogen into helium, then heavier elements up to iron in their cores under crushing pressure. Beyond iron fusion stalls, it's too energy intensive. So where do gold, silver, and platinum come from? One answer is neutron star collisions. When these ultra-dense stars smash together, they spew neutrons, which surrounding atoms capture, transforming into heavier elements via rapid neutron capture, or R process nucleosynthesis. The James Webb Space Telescope confirmed this in 2017, spotting gold in a kilonova's glow. But these collisions are rare, and ancient stars show heavy elements existed before most neutron stars could collide. Enter collapsars like the boat's star. When a massive star collapses into a black hole, its surrounding gas forms a disk. The black hole devours some matter, but the rest is blasted out in neutron-rich winds, potentially triggering our process to make gold. We hoped the boat would confirm this, but its spectrum showed no heavy elements. This absence is a game changer, suggesting collapsars might not be the gold factories we thought. Maybe the boat's low metallicity galaxy lacked the raw materials, or our models of our process and collapsars are wrong. This forces us to rethink how the universe's heavy elements formed, a question tied to everything from jewelry to nuclear reactors. The boat's photons didn't just dazzle, they defied physics. Traveling 2 billion years, they should have been scattered by cosmic dust, redshifted by the universe's expansion, or absorbed by background radiation. Yet tens of thousands arrived, some with energies so high they shouldn't have survived. How one wild idea involves axions, hypothetical particles linked to dark matter. Imagine photons morphing into axions, zipping through space unscathed, then flipping back to gamma rays in our galaxy's magnetic field. It's sci-fi stuff, but if true, it could rewrite particle physics, as axions lie beyond the standard model. I'm skeptical but intrigued. Axions are a long shot, no evidence yet, but the boat's data pushes us to consider bold ideas. Dark matter makes up 27% of the universe's mass energy, yet we know almost nothing about it. If the boat hints at Axions, it's a clue to one of cosmology's biggest mysteries. The boat's findings tie into a broader puzzle. Why do elements exist in the amounts they do? We measure this through stellar spectroscopy, analyzing starlight's absorption lines and meteorite analysis, revealing our solar system's early composition. These methods usually align, but there's a glitch: lithium. Big Bang nucleosynthesis predicts 3 times more lithium-7 than we see, and 1,000 times more lithium-6 than expected. This lithium problem suggests our models of the early universe are off. The boat with its missing heavy elements adds another layer. Maybe our nucleosynthesis theories need an overhaul. As a scientist, I love when data shakes things up. It's like finding a plot twist in a novel you thought you knew. The boat and the lithium problem remind us that the universe is a puzzle and we're still missing pieces. The boat wasn't just a flash in the sky, it was a wake-up call showing how little we know about the universe's building blocks from gold to dark matter. It challenged our models, sparked new questions, and reminded us that every cosmic event is part of our story. Here's the lesson: embrace the unknown. The universe is vast, complex, and full of surprises. Whether you're a scientist, a student, or just someone staring at the stars, let the boat inspire you to ask big questions. Where do we come from? What's out there? The answers start with curiosity. Thanks for joining me at the Voss Observatory. If this journey sparked your curiosity, check out my other videos on cosmic mysteries. A huge shout out to my supporters. Your passion keeps these stories alive. Until next time, keep looking up.